computational modeling of functional materials and technical reactivity using molecular dynamics, DFT, and wave function-based approaches. Thank you very much.
All right. So, good afternoon, everyone. Thank you very much for the opportunity to present my research today. So, I'm going to give a brief overview of our work and how our research in computational chemistry benefits from the high-performance computing resources provided by the CHPC. To start, just a few words about myself. I received my university degree from the High Chemical College of the Russian Academy of Sciences in Moscow. And I completed my PhD degree at Emory University in the United States. After that, I was a postdoc and Alexander von Humboldt Fellow at TU München, and later a senior researcher at Uni Bremen in Germany. And since 2019, I am a professor at the University of the Free State in South Africa. Here's a picture of our beautiful campus, and if you haven't visited it yet, I invite you to join us for one of our Free State PhyChem symposia that we organize every year, usually around November. So our research is in applied computational chemistry. It is strongly linked to the experimental research of our collaborators. And it includes the following subtopics or research lines, which are kinetics of gas phase radical reactions relevant to combustion, atmospheric and interstellar chemistry, luminescent organometallic compounds, heterogeneous catalytic reactions, confined subnanometric metal and metal oxide clusters, as well as functional materials relevant to electrocatalysis and battery research. So, for the first two research lines that deal with finite molecular systems, radicals, or charged complexes, we use the Gaussian software. It allows us to run density functional theory DFT-based or accurate post-Hartree-Fock wave function-based calculations, including ground and excited states. Environmental effects such as solvation can be also modeled with Gaussian. So some of these jobs are quite memory intensive, so we would not be able to complete them on our local UFS HPC cluster. Now, the last three subtopics deal with the surface reactivity on solid surfaces. For this kind of systems, we use the so-called periodic slab models, and we employ VASP and CP2K codes, which allow us to run either static computations or molecular dynamic simulations using methods based on density functional theory. So now, in the case of static calculations with VASP, in order to achieve reasonable speed with our relatively small systems, we need to use up to 96 cores per job. Whereas for AIMD simulations with CP2K, we need many more cores, so this is where we run into challenges. So in the following, I'm going to illustrate each of these research lines with an example application. This study has been done in collaboration with another theoretical group at Hyderabad, India. So here we deal with gas phase radical reactions relevant to hydrocarbon combustion, which means burning a fuel. And interestingly, the same reactions are also relevant to atmospheric chemistry. So just imagine that a fuel burns inside an internal combustion engine. Of course, this is a very complex process involving thousands of elementary reactions. Now here we deal just with a small but important subset of reactions relevant to incipient stages of hydrocarbon combustion, where a hydrocarbon radical R reacts with an oxygen molecule, forming different products. Here, the QOOH species denotes hydroperoxyalkyl radicals formed in the reaction. These are actually key intermediates which determine whether the overall chain reaction will undergo chain propagation, chain termination, or chain branching. Therefore, by understanding these trends, we should be able to better understand different ignition properties of different fuels. Now, this study is a collaboration with an experimental inorganic chemistry group at our department. Our colleagues have synthesized some luminescent dinuclear gold complexes with pincer-like ligands. So here the ligands are substituted diphenylphosphinoamines, where central substitute on the central nitrogen atom was varied. We varied the substituent, hoping that it could help us modify the pincer angle and also to tune the gold-gold distance as well as the luminescence properties of the complexes. However, this, as it sometimes happens, this didn't quite work out as expected, but instead we found that counter ions such as chloride or nitrate or hexafluoroantimonate do change the luminescence properties. So our study using time-dependent density functional theory allowed us to calculate spectral transitions, absorption, and emission of these complexes in good agreement with the experiment, and to explain the change in photophysical properties of the complexes based on the molecular orbital theory. This study, in collaboration with an experimental group at Freie Universität Berlin in Germany, is about a heterogeneous catalytic reaction. In heterogeneous catalysis, usually a catalyst is in the solid phase and the reactants are in the gas phase. They adsorb on the catalyst surface and undergo different chemical transformations. Now in this study, our catalyst is metallic gold, and the reactants are methanol and oxygen. So our collaborators studied the selectivity of partial methanol oxidation to methyl formate in ultra-high vacuum using molecular beams. Here the term selectivity refers to the preferential formation of a desired product, methyl formate, versus undesired over-oxidation to higher oxidation products. Our colleagues compared two representative gold surfaces, a flat gold 111 surface and a stepped gold 322 surface. And what they found was that much less of the desired intermediate methyl formate and much more of the undesired over-oxidation intermediate formate was formed on the flat gold surface. And our computational study helped to understand why this is the case. Here, ab initio molecular dynamics simulations were particularly helpful by showing that oxygen atoms on a gold surface can form extended chain structures, but only on a stepped gold surface and not on the flat surface. We have also shown that These chain structures are likely key intermediates determining the high selectivity of stepped gold surfaces in partial oxidation to methyl formate. Now, in this collaboration with another theoretical group in Madrid, Spain, we studied the stability and dimerization properties of subnanometric copper-5 clusters supported on graphene. Our study, with the help of ab initio molecular dynamics simulations, allowed us to study the stability of these particles on graphene surface. Interestingly, these particles, specifically the copper-5 ones, were shown to have special catalytic properties. However, a common problem with practical applications of such systems is a tendency of such small particles to sintering, in other words, agglomeration to form larger particles. So here we have shown that dye vacancy defects in graphene serve as efficient traps to stabilize copper-5 species and thereby preventing them from dimerization and sintering. Our results based on density functional theory predictions were supported by the analysis based on higher level post-Hartree-Fock methods based on based on coupled cluster theory and multi-reference perturbation theory, and also using electronic basis sets of increasing size. And finally, I would like to give an example of an application to electrocatalysis. In electrocatalysis, we use catalysts to modify the rates of electrochemical reactions. So one important electrochemical reaction is the so-called ORR, oxygen reduction reaction. It plays an important role in a variety of applications, for example, in fuel.
Your microphone just went dead.
So the best catalysts for ORR are platinum group metals, but nowadays researchers are looking for a replacement of precious metals for less expensive and more earth-abundant materials. And to this end, a very promising group of materials is called perovskites. Perovskites are mixed metal oxides with a special crystal structure shown here, which allows for a large variability in chemical composition. Also, by introducing small defects into perovskite structure, we should be able to tune their various properties. Now, this study has shown that by replacing some of the manganese atoms in the original perovskite with molybdenum, we significantly improve the electrocatalytic properties of this material and boost its performance for the ORR. Our theoretical calculation of the perovskite material has shown that doping with molybdenum decreases the activation barriers and makes the reaction energy profile more exothermic, thus leading to a decreased overpotential toward the oxygen reduction reaction. So now to summarize, our research spans a broad range of topics from gas phase kinetics to heterogeneous catalysis to electrocatalysis. It contributes to some of the global societal challenges such as sustainability energy harvesting and storage, as well as the development of new functional materials. We have a large network of collaborations with experimental and theoretical groups around the globe. And we produce high-quality research outputs that are regularly published in reputed international journals. Now, we are greatly thankful to the CHPC for providing us with the state-of-the-art high-performance computing facilities and for the excellent user support which enables us to use computational chemistry software and to run challenging calculations of molecular and crystalline systems relevant to chemistry. Finally, I would like to thank my present and former students and postdocs who contributed to this research. I'm thankful to our funders, DFG and RF, as well as the European Cost Action, COSI, Confined Molecular Systems. I thank Spanish and German supercomputing centers for providing computing time to some of our projects, as well as our local UFS HPC cluster. And I thank you so much for your attention.